This video is on escape velocity. Escape velocity is the minimum launch velocity required for an object to never return. To review, all kinetic energies have a sign that is positive, and all absolute gravitational potential energies have a sign that is negative. If we don't want to be bound to Earth, we need to have a total energy that is at least zero. This condition is what we focus on when we're finding the escape velocity. In the figure, a mass m is launched with escape velocity ve from the surface of a celestial body of mass m and radius r. We want a general expression for ve. Write an equation depicting the total energy m will have at the instant of liftoff. The energy this mass will have is its kinetic energy, 1/2 mv squared, but this is the escape velocity, so we're going to designate that with the subscript e, plus the gravitational potential energy that we can assign to little m, which is the opposite of big G, big M, little m, divided by the distance between their centers of mass, which is r. We're assuming that this planet has no atmosphere in launching it at its escape velocity. After m is launched at that speed, its speed thereafter will decrease with time. That's its original launch speed, and its speed is going to decrease as time goes on. And why is that? We would like a brief explanation. M's velocity vector points away from the planet, obviously, but due to gravity, its net force and thus acceleration vectors point toward the planet. So m's speed decreases with time. If the velocity vector and the acceleration vector point in the opposite direction, the speed of the object will be decreasing. So that's what's going to happen here. This launched thing is going to have its maximum speed at first, and then it's going to slow down as time goes on. For the conditions of escape velocity to be satisfied, m must reach a distance of r equals infinity. It's never going to return. Use those variables and let's depict the total energy that m will have when it's at a distance of infinity. So when it's at a distance of infinity, it's going to have a kinetic energy of 1/2 times m times v at r equals infinity. Let me just put a little subscript there, squared, plus negative big G, big M, little m, divided by r at r equals infinity. So I'm trying to indicate there that we are at a distance of infinity. All right, well, when it is at a distance of infinity, let's look at this right here. If r is infinity, then what happens to this term? If you take anything and you divide by infinity, you essentially get zero. And the velocity at a distance of infinity, remember, it's going to be slowing down, slowing down, slowing down, slowing down, slowing down the whole time. So if it's at a distance of infinity, basically its velocity is going to be zero, which means its net energy needs to be zero. And so what that means is if that energy total needs to be zero, let me go back to the previous page, then this energy right here also needs to be zero. What we're going to do then, I'm going to put a zero here on the left, and I'm going to take this negative term, put it on the other side like this. And if we solve that for the escape velocity, you can see that the mass of the thing that is launched is irrelevant. And I think we're going to get here that VE is going to equal what? 2gm over r square rooted.